Okay, let's go ahead and get started. So today is a very exciting day. So what we're going to study today is the Higgs mechanism, sometimes known as the Anderson-Higgs mechanism, sometimes known as the, what is it? I don't know. There's like 5 or 6 different names that it goes under. There's Engler, there's Brout, there's the guy at Brown. There's a bunch of people. So we're going to learn about the Higgs mechanism, otherwise known as many other different things, but for this class we'll call it the Higgs mechanism. And the basic idea of the Higgs mechanism is really what we're going to do is combine 2 things that we've already discussed in this class. Okay? So let's imagine that you have a theory with a global symmetry, such as a theory of electrons and positrons with a U1 rotation symmetry that relates those 2. Then, as we've discussed, there are really 2 interesting things that one can do with a global symmetry. So one of the things that we could do if we have our theory with a global U1 rotation symmetry, such as our theory of a massive Dirac fermion, is that you could gauge the symmetry. That leads you to electromagnetism. You make the symmetry parameter local, and then that turns into the gauge transformation of some vector field, and so you just follow your nose, and that naturally leads you to electromagnetism. The other thing that you can do with a symmetry is you can break it in the vacuum state. That is to say, you can consider a theory where you have a potential, and the minimum of the potential gives you a field configuration that is not invariant under the symmetry. And in this case, this also leads to a massless degree of freedom, not the gauge boson, but now a Goldstone boson. So the natural question to ask then, and I think this is a question that someone even asked last class, what happens if you do both? In particular, what happens if you have a symmetry which is gauge symmetry, that is spontaneously broken? So let's just consider a simpler case. That is to say, before getting into the details of non-abelian gauge theories and stuff like that, let's just consider scalar quantum electrodynamics. Okay. So here the Lagrangian will be, as it always is, you have a kinetic term for the gauge field, as well as a kinetic term for your charged scalar field, described in terms of a covariant derivative. So d mu phi is the partial derivative of phi plus I times the gauge field A times phi, with a coefficient E that is the coupling constant of the theory. And what I'd now like to do is imagine what would happen if we added some potential for our complex scalar field phi. So, for example, if you want the theory to be renormalizable, then V must be quartic in phi. And moreover, if you want to preserve this charge rotation symmetry, this gauge symmetry, then it has to be a function only of phi bar times phi, because that's the quantity that's invariant under a phase rotation. So the potential will have the form m squared times phi bar phi. Here, I'll write my phi bars first, just to make the analogy later on with Yang-Mills theory a little bit clearer. And then there'll be, in addition, some sort of quartic interaction term where you have phi bar phi squared. Sorry, I somehow can't write phi's very clearly today. And this is the most general renormalizable theory that one could write down, involving a complex scalar field coupled to a gauge boson. And if m squared is positive, then this will be the standard theory of scalar QED with a quartic interaction that we considered last semester. But, of course, in the space of possible Lagrangians, you could write down there's only a 50% chance that m squared is going to be positive. And when m squared is negative, the theory will be, the gauge symmetry, this U1 rotation, will be spontaneously broken. And the ground state will be some vacuum state where the expectation value of the scalar field in the vacuum state will be non-zero. So in general, because you have a U1 charge rotation symmetry, we could write this as some constant v times an arbitrary phase. And what I'm going to do is I'm just going to use the overall global charge rotation to set that phase equal to 1. Just to make our life a little bit simpler. Of course, one could also set it to be -1, or you could set it to be I, or anything else, and the results that you get would not differ. And here, the parameter v is just some number whose magnitude is given just by minimizing the function v that I wrote down. So that's just a straightforward exercise in finding the minimum of some quartic function. And its minimum looks like that. Okay. So far everything looks very similar to the discussion we had on Tuesday when we derived Goldstone's theorem. So what I'd like to do now is study the dynamics in a little bit more detail to see exactly what happens once this gauge field is in the game. But before I do so, let me pause and see if there are any questions. So if this gauge field weren't in the game, then what would happen is you would have a massless degree of freedom, which would essentially be the phase of phi. And if you were to expand phi, say, as in terms of two real fields, one of which I'll call rho, and the other of which I'll call chi. So rho here will be the fluctuation in the direction sort of perpendicular to, so if you want to think about this potential here, I couldn't really draw a Mexican hat last time, so the potential looks a little bit like this. Here, that's a bit better than what I drew last time. So that's a picture of the potential, so that's V. Is that better? It's a little better than what I drew last time. So here you have the minimum. And if you put the scalar field, say, in this minimum, then the massless Goldstone boson is just the phase of the scalar field. Whereas the massive part is the excitation in the direction transverse to the phase. So it's an excitation of the radial part of phi rather than the phase of phi. So if we just forgot about the gauge field and go ahead and put in this ansatz for phi in terms of its phase and its radial part, and then expand it around this ground state, then you would see that the chi field is massless. That's an exercise that we went through last time. And indeed, here just to remind you, let's just check that. So V of phi, if you write it out in terms of rho and chi, so I'll just tell you what the answer is. It's a straightforward exercise in algebra. Is quartic in rho, but is independent of theta, meaning of chi, meaning that chi is massless. Now, what happens now that we've coupled this theory to electromagnetism? Electromagnetism has a gauge symmetry, and under a gauge transformation, phi goes to phi times an arbitrary function of x, lambda, where lambda is the gauge parameter. So what we could do then is choose a gauge where chi is equal to 0 for all x. So if you found some solution with a particular value of chi, then you could always make a gauge transformation in order to set chi equals to 0. Okay. So you could choose a gauge where chi is always real, where phi is always real. And this is a convenient gauge for the purposes of understanding the physics of what's going on here, known as unitary gauge. Now, for the purpose of computing Feynman diagrams, unitary gauge is okay for tree-level Feynman diagrams, as we'll see, but perhaps by the end of this class we'll also discuss loop diagrams where unitary gauge is not so helpful. And the question you might then be asking yourself is that by making this gauge choice, we appear to have removed a degree of freedom from the theory. So where does that degree of freedom go? In order to understand where that degree of freedom goes, let's just investigate the kinetic term in a little bit more detail. So in this unitary gauge, the kinetic term for phi, well, what is that? That's d mu phi bar times d mu phi. So just plugging in the definition of d mu phi. So d mu phi is partial phi plus a correction term, which was phi. So what was phi? So it was, here, let me just, so it was phi so I'll just write it just to save myself a couple steps. Well, okay, I'll just write it all out. So phi times a mu, quantity squared. And so then let's insert our ansatz for phi into this. And what will you get? Well, if we're in a gauge where chi is equal to 0, this just turns into d mu of rho minus i.e. v plus rho times a mu quantity squared, which is, expanding that out, the standard kinetic term for the field rho, which was the radial part of phi. Then there's a cubic term, which cancels, plus a quartic term, which is proportional to e squared times v plus rho a mu a mu. And what we're most interested in, sorry, quantity squared. What we're most interested in is the case where is just the kinetic term in the Lagrangian. And so if you stare at this term for a second, you'll see that this leads to a term that looks like e squared v squared a mu a mu. Okay. So what, plus a bunch of other terms, in particular a quartic and a cubic and a quartic interaction between the gauge field A and that radial field rho. So what is this term? This is a mass term for the gauge field A. Okay. So what's going on here? So this is known as the Higgs mechanism. And the basic idea is that whenever you have a spontaneously broken gauge symmetry, the corresponding gauge boson becomes massive. Now, in thinking about this, it's a little helpful to count the degrees of freedom and to make sure we understand exactly what's going on here. So if you think about the unhinged theory, if the mass squared is positive and you're just expanding around the phi equals 0 vacuum state, then you have 4 degrees of freedom. Phi is a complex scalar field, and we study the small fluctuations of phi and quantize them. So that has 2 real degrees of freedom. And likewise, the gauge field has 2 real degrees of freedom, which are the polarizations of A mu. So in particular, if you think of A mu as a set of 4 functions labeled by that index mu, then one of those is removed by the equations of motion, and another is removed by gauge invariance. However, in the Higgs phase, if you use this unitary gauge, then phi just is reduced to 1 real degree of freedom, which we called rho. But A is now a massive gauge boson, so it no longer has the full gauge symmetry, which required us to throw out the longitudinal polarization of the photon. And so indeed, as we'll see, I'll work this out in a bit more detail in just a few minutes, A is now going to have 3 real degrees of freedom, because the longitudinal polarization of the gauge boson, the polarization where the polarization vector of the epsilon is proportional to the direction of motion, kmu, is proportional to the momentum kmu of the gauge boson, now becomes physical. So we really have 4 degrees of freedom, 4 real degrees of freedom no matter what we do. The point is that when we work in this unitary gauge, we've shuffled around the degrees of freedom so that now it looks like phi only has 1 degree of freedom, but the gauge field has 3 degrees of freedom. In fact, how we distribute the degrees of freedom between that complex scalar field and A mu is a little ambiguous. Really, it's a gauge-dependent statement. You know, you could always make a gauge choice to remove the phase of phi, but that means you have an additional degree of freedom in A, or you could work in some different gauge. For example, if you work in R psi gauge, you know, the degrees of freedom will look a little bit different. This is something we will hopefully get to at the end of class. But no matter how you shuffle things around, you know, real life doesn't depend on gauge transformations. So no matter what we do, we always have 4 real degrees of freedom. There's something that, there's a sort of slogan that people sometimes say in order to remember, a mnemonic that people use to remember what's going on here. And the mnemonic that people use is that when you spontaneously break a global symmetry, you get a Goldstone boson. And what's happening here is that the gauge field is eating the Goldstone boson, and it's getting fat. So what was previously regarded as a Goldstone boson, the phase of chi, is now regarded as the longitudinal polarization of a gauge boson, which, and a vector field can only have a longitudinal polarization if it has a mass, you know, if you've broken the gauge symmetry. Now, in some sense, the statement that I'm breaking the gauge symmetry is a little bit of a fake. It's more like I'm fixing a gauge, a unitary gauge, and that's using up all of my gauge degrees of freedom. Any questions on this so far? Yes.
So, if we look at the calculations for the next term of the scalar field, then if we weren't any physical reason to expand the field in R plus V,
Right.
the calculation suggests that if we arbitrarily expand the field, then we get a master.
That's right. I mean, yeah. Let's put it this way. If you want to study the perturbations, very small fluctuations of your field around the ground state, then the sensible thing to do would be to expand your field, where did I write it? To expand your field in this way. And then rho and chi would be very small if you're studying a very low energy excitation around your ground state. And then indeed, when you do that, what I'm doing here, plugging that ansatz into here, is really just studying the spectrum of perturbations, or more specifically, I'm studying the dispersion relation, the relation between energy and momentum, for those small fluctuations around the ground state. But as you say, there's no rule that says that I have to use this particular way of decomposing my scalar field or this particular gauge choice. I could stick with my original complex scalar field if I wanted to. But now you would just have to keep in mind that the low energy excitations would not be small phi, but rather small deviations of phi around your non-trivial minimum.
But in general, if I was to relabel my field and express it somehow differently, then if I say that my phi of x is something to that a constant plus another field, not necessarily considering the small fluctuation, then the calculation for d mu phi suggests that the logis have a mass for the a mu.
That's right. That's right. I mean, it's absolutely correct. Whenever you have some dynamics that makes your scalar field have a non-trivial vacuum expectation value, take a non-trivial value, that will give you a mass to your gauge field.
Okay. But
Now,
it's fake because I can really...
Well, whether it's fake or not is a matter of language. One can always, the point is, how should I say this? It's not fake. We've chosen a gauge where your vector field now has a mass. Okay, and that's just the dispersion relation you get, and it affects the Feynman rules and affects the dynamics and all of that stuff. What I'm saying is that there are other ways of writing it. So you could also write it where you don't have a longitudinal polarization of your gauge boson, but you do now have the Goldstone boson. But the point is that you would now have interactions between that Goldstone boson and the gauge boson, which effectively are the same thing. I don't know if I'm being completely clear here. The action is still gauge invariant, but phi now is transforming. You're looking at a solution that's transforming under those gauge transformations. Okay? And so that affects the dynamics. And the sort of quick and dirty way of understanding the dynamics, the quick and dirty way of understanding the dynamics is really quite easy. I mean, you start with this action that we've written here. You assume that V of phi sets phi to be something non-zero. And then just forget about the fluctuations of phi for a second and just look at the dynamics of A. And then what you'll see is that when you expand this guy out, you have a term, this term here. When you square that term, if phi is just equal to a constant, this just gives you a mass term for A. It gives you an a mu times E squared times the value of phi squared. So whenever you have some dynamics that makes the value of your scalar field non-zero, you'll get a Higgs mechanism. I mean, this appears all over the place. So for example, this is superconductivity, as we'll see in a second. And you can use this model to make some quantitative statements about superconductivity. This is also the theory of electroweak, electroweak symmetry breaking for SU2 times U1, as we'll get to next week. There's also even a sense in which this is what the theory of inflation is, okay? Where there, the gauge symmetry is the time translation symmetry of general relativity that's being broken by the fact that you have a field, a scalar field, just as in this case, which is now called the inflaton. And it has some non-trivial dependence in time, which is breaking that symmetry. So this is a very sort of general piece of physics. And as always, when you have a gauge symmetry, that means you can shuffle the degrees of freedom around however you like. And so for the purposes of doing this sort of perturbative analysis, I'll just use this unitary gauge. Good question.
when you expand the kinetic term for the scalar field,
Uh-huh.
I didn't quite see what happened to the cross terms. Where did they go?
That was supposed to cancel if I did everything right.
Oh, okay.
They were just
Yeah,
supposed
oh
to
yeah,
cancel
one of them is,
out.
right, okay, good.
Because it's a real plus imaginary there.
Okay, yeah, cool.
Right. So it's the sum of the real part squared plus the imaginary part squared. Sorry, there's supposed to be a, I guess I should really put absolute value squared.
Yeah.
Okay, sorry about that. Okay, so they're supposed to cancel out. Good. Thank you for that. Important clarification. Okay. So, it's reasonably straightforward then to extend this to non-abelian gauge theories. So I'll just work out a simple example here, and you'll work out a slightly more interesting example on the problem set. So let's imagine that we have a scalar field which transforms in some representation of the gauge group G. Then the gauge covariant derivative is the usual partial derivative plus a covariant derivative term involving the representation matrix, the representation matrix in representation R. So here I is an index that labels the fields in this representation. So for example, in the fundamental representation of SUN, I would go from 1 up to n, and phi would be a complex field because it's a complex representation. And then you imagine that you have some potential or some other sort of dynamics such that in vacuum, that is to say the lowest energy solution of the potential, phi is going to be non-zero. So we could take it to be proportional to some vector vi, where again this is not a space-time vector, but a vector in your representation space. Then expanding out around this vacuum solution for phi, so we have the kinetic term, e mu phi squared, and if you just plug in that value of phi, that value of phi in vacuum, what will you get? Well, you'll get some mass term for the gauge bosons that we can call m squared AB. So m squared AB is found just by plugging this thing here into our formula, into our kinetic term here, and using the form for that interaction. So here we're just going to ignore the partial derivative of phi for a second and just square this term. So what do you get? Well, you'll get something like g squared times vi ta tb ij vj. I guess I'm totally bad about whether I write my indices upper or lower, but you know what I'm saying here. I guess, yeah. If we're in a complex representation, so this is the expression, so this MAB is known as a mass matrix you know, it's not necessarily diagonal. but one could always do a change of basis to make it diagonal. And in fact, sometimes people write this slightly differently. Sometimes people will actually write this not as the product, but rather as the anti-commutator. And the reason why you can write it as the anti-commutator is that this m squared ab is multiplying this object here, a mu b, which is symmetric in a and b. So you can always symmetrize m squared ab. That's a nice thing to do because a mass matrix, well, you know, it's sort of most natural to view that as a symmetric matrix. Right? And so this is a d by d matrix. So here I've written the form of the mass matrix if you have a real scalar field and with a complex scalar field, so corresponding to some complex representation of the gauge group, you would have a very similar expression, except you would have the complex conjugate of one of these vectors here. Is this crystal clear, hopefully? Nothing too fancy. Now, the point, really, in writing down this mass matrix is that from this, one can see reasonably clearly that only those symmetries, or let us say, only those gauge bosons corresponding to spontaneously broken symmetries will get masses. So to say that a little bit more clearly, so let's imagine that we have our real scalar fields transforming in some representation given by some representation matrices TA. Then under a gauge transformation, so the variation of phi is given by a gauge parameter theta A times TA ij phi j. So that's under a gauge transformation. Then the symmetry is broken. The gauge symmetry is broken for those gauge transformations such that the gauge transformation of phi in the vacuum is not equal to 0. So some of the gauge symmetries will be broken and some of them will not. And only those gauge bosons, sorry, I guess I said this here, only those gauge bosons that correspond to those broken symmetries will get a mass. So let me do a simple example of this, just to make this clear. So let's consider the case of SUN with phi transforming in the n-dimensional fundamental representation, which is a complex representation. And let's assume that we have some potential so that the minimum is at phi I equals Vi. And just to make life simple, just as in the case of electromagnetism, I could use my symmetries to set phi to be real. Here, what I'm going to, in vacuum, what I'm going to do is set Vi to be non-zero only if I is equal to n. Then that means that only those generators with non-zero, sorry, let's say such that TA, let's call it Ni, or TAIN not equal to 0 are broken. So remember that for SUN, these TAs are traceless Hermitian matrices. Okay? And V is an n-dimensional vector whose last component is non-zero. So you're asking, when does the matrix T, this traceless Hermitian matrix, multiplied by V, give you something non-zero? Well, it gives you something non-zero if T has some, non-zero entries in its last row or last column. I guess technically speaking, it would be its last row, but because T is symmetric, it's the same, or Hermitian, that's the same as saying its last column as well. So what does that mean? That means that of the original SUN gauge bosons, some will remain massless and some will not. In particular, the ones that remain massless correspond to the unbroken symmetry. Those are the gauge bosons that correspond to the TAs where the last column and last row are all equal to 0. So what gauge group does that generate? Well, that's the gauge group SUN minus 1. You know, an SUN matrix, but if you throw away the last column and the last row, it can be thought of as an SUN minus 1 matrix. So of the original SUN gauge bosons, an SUN minus 1 is unbroken. But you still have, but n of the gauge bosons now become massive. Corresponding to those traceless Hermitian matrices TA, the n-dimensional space of traceless Hermitian matrices TA, whose last column is non-zero. Is that clear? Is that any questions on that? You know, if you want to, so if that's not 100% clear, don't worry. On your problem set, you're going to work out the analogous case for an adjoint scalar field instead of a scalar field transforming into fundamental representation. So maybe just to make this a little bit more clear, we can talk about the field content of this Higgs SUN gauge theory in a little bit more detail. So in particular, these massive vector fields are going to be charged under the unbroken SUN minus 1. So in particular, can anyone tell me, let's see if you guys grok this. Can anyone tell me what representations of SUN minus 1 they'll transform under? Okay, let's just start working this out. So the gauge bosons can be regarded as, the original gauge bosons were n by n matrices, okay, traceless Hermitian n by n matrices. And the ones that were unbroken transforms there. But then the gauge bosons that live here will be broken, will be masked up. And so you'll get n massive vector bosons. And can anyone tell me how, so what do you get? You get one gauge boson here, and you get a column of gauge bosons there. Can anyone tell me what representations of SUN minus 1 they transform under? You had a very similar problem on the problem set 2 last week. Maybe it was the week before. We had SU3 and we broke it down to SU2 in exactly this way. Well, let's give you a little hint. So this is an n minus 1 by n minus 1 matrix. This is an n minus 1 dimensional column vector. So it transforms in the n minus 1 representation of SUN minus 1. Okay. And this guy here is, well, there's only one of them. And so it's in the singlet of SUN minus 1. It doesn't transform under the SUN minus 1. Is that, I mean, is there a way that I can explain this more clearly? I'm trying to think if there's a way I can explain this more clearly if this is not true. I mean, you did work this out in your problem set last week, right? Am I correct in understanding this? You started out with the SU3, and then you looked at the SU2, and then you had a column vector. Is that right? Did I give you this problem, more or less? Okay. If this is not complete, okay, since this is not completely and explicitly clear, what I recommend that you do is work out explicitly how it is the gauge bosons transform in this case. I guess you're going to have to do this for problem 2 that I just handed out in the more complicated adjoint case. But the point is that the gauge bosons A mu transform under a gauge transformation. You know, they transform as an FABC, theta B, A, C. And where these FABC, okay. So these FABCs are the structure constants of the gauge group, but can also be regarded as the representation matrices in the adjoint representation. So if you think about this, that means that you can think about a field in the adjoint representation as an n by n Hermitian matrix. Indeed, all a gauge field is an n by n Hermitian matrix. And so this is saying that the variation of A, when you think about it as an n by n Hermitian matrix, is proportional to the commutator of your gauge parameter with A when you regard it as an n by n Hermitian matrix. And then if you just take A and you write it as a sort of n minus 1 block with a little column vector sitting here, and you ask how that column vector changes when you conjugate the block, well, or when you do this commutator, well, it transforms exactly like a column vector being multiplied by a matrix. That's something that you all should work out. Is this more or less hopefully clear? Okay. Don't worry, you're going to have to understand this to do the problem set for next week. So don't worry about not understanding this, because you're going to. Okay. And then it's straightforward to go ahead and work out the masses of these gauge bosons. So for example, just plugging into the kinetic term, gives you the masses of these gauge bosons. And so, for example, the n minus 1 column vector gives you a mass that is proportional to GV, and the singlet, the one-dimensional representation, the thing that doesn't transform at all under the SUN minus 1, sorry, I guess that's supposed to be a mass squared, has mass squared, well, this is something that you just have to calculate, so I'll just quote the answer for you. It's some function of n times GV. Okay. So if you didn't already realize that n minus 1 of those vectors were related by some symmetry, the fact that they all have the same mass would be a little clue. You see, if you have a field theory and a bunch of fields all have the same mass, then that's a hint that you could rotate among them, and that's a symmetry. So the point that I really want to make clear is that the mass matrix, what we called M squared AB, is a dimension of the gauge group by dimension of the gauge group matrix. But it has a lot of zero eigenvalues. It has the dimension of the group H, 0 eigenvalues, where H is the group of unbroken symmetries. So the general story is that when you have a gauge theory with a gauge group G that is spontaneously broken, down to H, you end up with a gauge theory with gauge group H with a bunch of massive gauge bosons, or I should say massive vectors, that are charged under the unbroken gauge group H. And we saw that explicitly up above, that if you have an SUN gauge theory that gets broken down to SUN minus 1, then some of the gauge bosons, the SUN minus 1 gauge bosons, remain massless, but those other n gauge bosons get a mass, and they look like charged particles with respect to that unbroken gauge theory. It might be, actually I would recommend this. I should have done this on a problem set. It might be worth working this all out explicitly for the case of SU2 broken down to U1, or SO3 broken down to U1. So last class we worked out, when we talked about Goldstone's theorem, the case where you have a complex vector in the two-dimensional representation of SU2, or maybe it was in the three-dimensional representation of SO3. I think that was the one that I talked about. And there you have a U1 symmetry which is unbroken, and the remaining two gauge bosons got a mass, would get a mass in this case. Okay, is this all more or less clear? Any questions? We should pause here for questions. I guess the thing is that this group theory language can be a little bit unfamiliar at first. All this representation theory matrices and mucking around with it. But it's all actually pretty easy once you get used to it. Trust me, all this is actually easier than what we've been doing for the last couple of weeks. Good. Any questions? So maybe something that would help make this a little more relevant to you would be to step back from all of the fancy non-abelian gauge theory and stuff like that, and use this to study a system that you all already probably know at least a little bit about, namely a superconductor. Okay. So in particular, the Landau-Ginzburg theory of superconductivity is nothing more or nothing less than the Higgs mechanism for a U1 gauge field, namely the Higgs mechanism for electromagnetism. So what's the basic idea? The basic idea, as I believe was originally proposed by BCS, was that in a superconductor, electrons, which are charged spin 1/2 particles, can form pairs, known as Cooper pairs. And these pairs form because of some strong interactions between the electrons, because of some strongly coupled dynamics that we may or may not understand very well. But the point is that these electrons, which were fermions that had spin 1/2, once they pair up, they can become scalar bosons. But because they have charge, they're now charged scalar fields, which we will denote phi. And then, at long distance, the theory should be described by some sort of effective field theory. And one should include, in the effective field theory, all of the relevant terms in the Lagrangian that would appear in long-distance effective field theory. Of course, Landau and Ginzburg did this before the renormalization group, really, or perhaps simultaneous with some ideas about the renormalization group, but certainly before Wilson. So they may not have used this language. But the idea is that they just said, well, you have a charged scalar field coupled to electromagnetism. And so what sort of Lagrangian would you get? Well, you would get the Lagrangian of a scalar field coupled to electromagnetism, which at leading order has a quadratic term, a quarter term, a quartic term, and a bunch of stuff that's not going to really matter. From the effective field theory point of view, these would all be irrelevant interactions. And the idea is that this is really the parameters in this action are functions of temperature. So really what I'm writing down here is not an usual action in the sense that we've considered it so far in this class, but rather a free energy. And as you dial the parameters in the theory, as you dial the temperature, for example, the free energy will change. And the idea is that above the superconducting phase transition, we're in a phase where the vacuum expectation value of the scalar field phi is equal to 0. And below the superconducting phase transition, you're in a phase where the vacuum expectation value of phi is non-zero. As we discussed last time, if you just forgot about electromagnetism, you would have in this superconducting phase a massless excitation, which would be the low energy long wave, which would be the fluctuations of this order parameter phi. In other words, you would have some Goldstone boson, which would describe the excitations of this charged scalar field around its vacuum values. And this scalar field would have to be massless when you expand around this value because of Goldstone's theorem. But now, of course, we're taking into account the fact that the scalar field is charged because it's formed of a pair of electrons. And so that means that below the phase transition, good old-fashioned electromagnetism is Higgs. The electromagnetic field in a superconductor is massive. Now, of course, at a truly microscopic level, on scales very small compared to the interatomic spacing of the superconductor, electromagnetism is really massless. Okay, it's just electromagnetism. But on long-distance scales, where we have to take into account the interactions of the electromagnetic field with this field phi, electromagnetism will be effectively massive. So what do we know about massive fields as opposed to massless fields? Well, we know that correlations of two-point functions, say, of massive fields fall off exponentially with distance, whereas correlation functions of massless fields fall off power law with distance. What does that mean? That means that the electromagnetic field cannot penetrate a superconductor. If you turn on a magnetic field in the presence of a superconductor, then that magnetic field outside the superconductor will fall off exponentially once it's inside the superconductor. So this is a very famous, perhaps one of the most famous features of a superconductor, which is known as the Meissner effect. So magnetic fields are expelled from a superconductor. Now actually, using this Landau-Ginzburg model, we can take this logic a little bit further. So actually, electromagnetic fields can penetrate a superconductor, but when they do, they'll fall off very quickly. They'll fall off exponentially. And so you would expect an electromagnetic field to penetrate a superconductor at a certain length, L, which is determined by the mass of electromagnetism in the superconductor, which is determined by this Higgs mechanism. So this length scale, which determines how far into a superconductor the electromagnetic field can penetrate, is known as the London penetration length. And we're now in a position to calculate this. So remember that the electromagnetic field now has a mass. What is that mass? Well, it was the gauge coupling squared times v squared, the vacuum expectation value of the electric field. And what is v? Well, v, so we computed it up here. Let's see if I can find that. So there was v, it's right there, square root of the square root of m squared over lambda. And in the present context, m is this parameter a, and lambda is this parameter b. So this will be the square root of a over b. I'm just neglecting factors of order 1 here. So that the penetration length, so just by dimensional analysis, you know that length is 1 over the mass of the gauge boson. If you wanted to be a little more precise, you could just calculate the two-point function of a massive gauge field. It would fall off exponentially with distance, and the coefficient of that exponential is the penetration length. And just by dimensional analysis, it has to be set by the only dimensional scale in the theory, which is the mass of the gauge field. So what is that? That's 1 over e times v, or the square root of b divided by e times the square root of a. Now, Landau and Ginzburg took this one step further, and they said, well, we have the superconducting phase transition, above which phi is equal to 0, and below which phi is not equal to 0. That means that that coefficient a must change as we dial the temperature. So let's just do a Taylor expansion near the superconducting phase transition and expand a in powers of t minus t critical, where t critical is the critical value of the temperature. And we know that near the phase transition, where the temperature is at its critical value, you must be able to expand that coefficient A in a power series in T minus T critical. So you can write A as something times T minus T critical. And B will just be given by some constant at leading order in its Taylor expansion. So that means that this penetration depth will go like some constant. So let's just forget about the constant, but its scaling with temperature will be like 1 over the square root of T minus T critical. So what is this telling you? This is telling you that when you're just below the superconducting phase transition, the penetration depth of an electromagnetic field into the superconductor goes like 1 over the square root of the difference between the temperature and its critical value. And as you heat up the superconductor, T will approach Tc, and the electromagnetic field will penetrate deeper and deeper inside the superconductor. So, just as a historical note, so this theory was known before Higgs. So this theory was known in the condensed matter community before it was known in the particle physics community. So in the particle physics community, the Higgs mechanism was used to describe how the electroweak gauge bosons get a mass. And so that was the Higgs, the spontaneous breaking of a non-abelian symmetry. But as far as the spontaneous breaking of an abelian symmetry, of a U1 gauge symmetry, in electromagnetism, this was known in the condensed matter world before it was known in the particle theory world. And so for this reason, so in the condensed matter world, this was sometimes called the Anderson effect. And so this is why the Higgs mechanism is sometimes called the Anderson-Higgs mechanism. And I think that's a pretty fair characterization. And I think there's actually a lot of interesting, people who study the history of physics talk a lot about exactly how it was this knowledge of the Higgs mechanism made its way from the condensed matter community into the particle theory community. I mean, in some ways, it was sort of an amazing leap to realize that essentially the Higgs mechanism is the statement that we live in a superconductor. That the empty vacuum that we see around us is really a superconductor. It's not a superconductor of the electromagnetic force like it is in the superconductor you would build in a lab, but it's a superconductor of the nuclear forces, of the weak nuclear force. Pretty amazing story. Okay. Let me see. Are there any questions before I proceed? Have you guys seen this theory of this? I mean, you guys must have studied superconductors at some point in your lives. So hopefully the statement that electrons form pairs and all that stuff is not a completely new statement. Question?
Yeah, so do electrons also form interesting spin-1 quasiparticles?
I believe they do.
Do they do anything we care about?
That's an interesting question. I don't know. I'm not an expert in that subject, so I don't know. My guess is yes. My guess is that there's probably some interesting massive vector excitation coming from pairs of spin-up electron rather than spin-up, spin-down forming a scalar field. I don't actually know. That's a great question. Good. Any other questions? So, what I'd like to start doing in the time I have remaining is I'd like to start thinking not about the classical theory of spontaneously broken gauge symmetry, but But what happens when we study the quantum theory? So now we need to quantize one of these theories. And the important distinction is that when we quantize, we're going to need to expand around the vacuum with some sort of broken gauge symmetry. So let me just start, because I think it's the easiest, by working in unitary gauge. If we study this in more detail, and I'll have to decide how much time we have to do this, we may end up working in R psi gauge. But as far as tree level calculations go, where we don't have to worry about ghosts and all of that nonsense, unitary gauge is fine. And so in this case, and let's also just work with electromagnetism, just to make life simple. And so in unitary gauge, the photon now has a mass, which is equal to g times b. And so the Lagrangian is now the standard Lagrangian of electromagnetism plus this mass term. Now, when we studied the quantization of electromagnetism in QED, we didn't include a mass term for the photon because that would break gauge invariance. But there's really not too much different that happens when you include a mass term, except that you have one more degree of freedom because you no longer have the gauge symmetry of the theory. So just to work this out a little bit more explicitly, what is the equation of motion? So the equation of motion, well, you have a kinetic term and the equation of motion says that that kinetic term acting on A has to be equal to 0. So this is exactly as it was in electromagnetism, except that now we have a mass term here. And again, I don't seem to be able to square my masses. Do that. It's mass squared. So this equation of motion, at first sight, looks rather complicated. So we have this piece here, which looks a little bit like the scalar kinetic operator, but then this more complicated piece, which came from the F mu nu. However, it turns out that you can actually simplify this a little bit. So to simplify, just act with this equation, act on this equation with d by d x mu. Okay? So contract that equation with d by d x mu. What do you get? Well, from this term here, you get d by d x nu, you get d nu of a nu, and you get, sorry, I should say it a little more carefully, you get partial squared of d nu a nu. And when you act on this term, what do you get? Well, you get partial squared of d nu a nu, except that this term had a minus sign, so those two terms cancel out. And what you're left with is m squared times d nu a nu is equal to 0. So we've automatically killed one degree of freedom in A. So in Fourier space, we would say that K mu contracted with A mu is equal to 0. Just like if we had a massless gauge boson. And once we know that d nu of A nu is equal to 0, you can simplify that term. And what does it look like? Well, it's just minus d squared plus m squared A nu is equal to 0. So what is that? Well, that's just precisely the equation of motion of a scalar field. So when we quantize A mu, nothing fancy is going on here. So A mu looks like a scalar field, or rather I should say a collection of scalar fields subject to the constraint that in Fourier space K is perpendicular to A. So for example, if we want to go ahead and quantize we can just expand in modes so that, for example, if you wanted to expand in raising and lowering operators, you now need to sum over 3 polarizations, which I guess, should I label them? What will I label them by? I guess I'll label them by lambda. That's what I have in my notes. So you have an integral d3k, and then you'll have 3 polarization vectors. So let's call it epsilon mu lambda of k, a lambda of k. So that'll be the lowering operator that destroys a vector field with polarization lambda, plus the Hermitian conjugate involving a creation operator, a lambda dagger. And this parameter lambda labels polarizations. And the only constraint we have is that lambda goes from 1 up to 3. And we have the condition that epsilon lambda mu contracted with k mu has to be equal to 0. And this should be contrasted with the case of a gauge theory, where we only had 2 physical polarizations rather than 3. And so then it's straightforward to work out the to work out a complete basis of these polarization vectors. Okay. So for example, you could go to a frame where the gauge boson is at rest, or I shouldn't call it I keep calling it a gauge boson, where the massive vector field is at rest. Okay. Now because the particle has mass, you can go to its rest frame. You can't go to the rest frame of a massless particle, but you could go to the rest frame of the massive particle. Then you could work out explicitly whatever basis of epsilons you like. Okay, so for example, you could have an epsilon x, an epsilon y, and an epsilon z. And typically, we'll use a basis where, for example, epsilon lambda mu contracted with epsilon lambda prime mu will be equal to 0 unless lambda is equal to lambda prime. So that's just the statement that these 3 polarization vectors will be chosen to be orthogonal. And then, just as in the gauge boson case, we have this nice formula for what happens when we average over polarizations. If you average over polarizations of a massive vector, again, you'll get something proportional to g mu nu. But if you work out the details, and this is easiest to do, I suppose, by just, say, going to the rest frame of the vector field and writing out an explicit basis of vectors, you'll find that you get a formula like this. So I believe in one of the problem sets last semester you derived this formula for a massless gauge field. And this is just a very similar formula for a massive vector. And the quantization is completely straightforward. So for example, the Feynman rules are reasonably straightforward. In particular, the propagator is something, I guess, I don't remember what we called it, pi mu nu, delta mu nu? Maybe we called it pi mu nu, I forget. Well, let's call it delta mu nu now. Well, what is it? Well, it's just 1 over k squared minus m squared times some tensor structure. And just as in the case of electromagnetism, that tensor structure is exactly the same thing that appears in this equation. So that propagator, I suppose, is easiest to work out if you just look at this differential operator here, and then you invert it. So as usual, propagators are found by inverting the differential operator that appears in the equations of motion in momentum space. So the Feynman rules that we write down in unitary gauge are perfectly straightforward and perfectly fine for tree level diagrams. When you work with loop diagrams, it turns out that we still need to be careful to take into account gauge invariance. In particular, as we learned, the theory is still gauge invariant. The point being that we now have a field that's transforming non-trivially under these gauge transformations. And so that means that you still need Fadeev-Popov ghosts, but the dynamics of these Fadeev-Popov ghosts is going to be a tiny bit different in order to account for the fact that you now have a vacuum expectation value that's breaking your gauge symmetry. So actually over lunch, I asked Guy, who teaches our standard model class, whether they actually, in the standard model class, ever do loop calculations with spontaneously broken non-abelian theories. His answer was no, that all of the calculations they do in this class, that class were tree level, which is not to say that these things aren't important, but which is to say that it's not something that we necessarily need to dwell on too much in this class. I'm just about out of time here, so I don't think I'm going to do that this class. And we have 2 more lectures left, so I'm going to have to this weekend write my lecture for next week and decide exactly how important it is to study the quantization of these non-abelian theories at the loop level using RSI gauge. Maybe I should stop here and see if there are any questions. So on your problem set for next week, you'll have a couple of problems that will let you hopefully understand in a bit more detail both Goldstone's theorem and non-abelian gauge theories with broken symmetry. Yes, question.
So the sign of m squared
Mhm.
not change if we not normalize, like for example, go from positive to negative. So we have things. I'm thinking about how much the sign of m squared
Well,
can change dynamically.
No, I mean, it can change dynamic. I mean, there's no rule that says that it can't change. I mean, if you think about the case of the superconductor, there we have a parameter, which is an additional parameter, which is the temperature on which the couplings behave, dependent. But there's no rule that says that if you might be studying the theory at low energies where the mass squared is positive, but that as you run up to high energies, the mass squared might turn negative. In fact, this is not a matter of simply academic interest. Well, I suppose it is academic, but this is a matter of sort of interest because the present value, so the present value of the Higgs mass is suspiciously close to a value where something like that might actually occur. Where as you run up to high energies, it won't be the mass squared term that changes sign, but some other term in the effective action will change sign and make it unstable. So I don't think, there's no, in principle, reason why this sort of thing couldn't happen. RG4.
So by quantum corrections in general,
Quantum corrections are quantum corrections. You know what they are.
when we quantize our quantum superconducting theory, then we take it as it is and then quantize it, that's just like I did here.
That's right. That's right.
You
Yeah.
can describe it, the quantization of the process of well change.
Well, let's put it this way. When we quantize, if you're studying perturbation theory, then what you want to do is study small excitations around some classical state. Now, of course, if you were really powerful, you wouldn't need to use perturbation theory, and so you could just do whatever you're going to do. But in practice, we have to use perturbation theory. And so you would quantize expanding either around state with broken symmetry or state with unbroken symmetry, depending on which one is the, you know, the stable solution to the classical equation of motion. Good. Okay. See you guys on Tuesday.